Today we are going to see the practical link budget design using the path loss models. There are two approaches regarding this link budget. One is the empirical approach, another one is the analytical approach. In an empirical approach, we will be drawing some curves. Depending upon the data available, we will be drawing curves. In analytical approach, mathematical expressions will be there, and by using those expressions and providing some data, you can calculate some data. So this analytical approach takes into account all the propagation factors, whether we are familiar or unfamiliar, through the actual field measurements. Because in an open space environment, this can be carried on. So the known as well as unknown factors are taken into account. Next is path loss models. So the path loss model is used to find the amplitude of the signal at the receiver. This amplitude of the signal will be a function of distance. As the distance varies, the amplitude of the received signal will vary. Then this path loss models is used to predict the signal to noise ratio for a mobile communication system. So in path loss models, we are not only going to measure the signal strength as a function of distance, we will be also measuring the signal to noise ratio for that particular system. Log distance path loss model. So theoretical and measurement based propagation models says that the received in log distance path loss model, both theoretical and measurement based models are available. These two models says that the received signal decreases logarithmically with distance. Whether you are carrying out the measurement either in the indoor or outdoor environment, in both the models, theoretical as well as measurement based models. Theoretical means you will be having some mathematical expressions, you will be substituting some value, and then you will be getting the received signal strength. In measurement based models means at different environments, at different distances, you can transmit some signal and you can measure the signal by using some power meters. So both these models says that the received signal at the receiver portion decreases logarithmically with distance. In here, the average path loss for any transmitter receiver separation depends upon the distance. That is, as the distance varies, the average path loss for a particular, for any separation, it is a function of distance. So when the distance varies, this path loss component will be. Path loss component is represented by n. So this is the equation that is used to calculate the path loss. This bar indicates that it is the average value for a group of different measurements or different TR separation measurements. This path loss is a function of distance. So D is written in the bracket. So this path loss is directly proportional to the D by D naught to whole power n. D is the TR separation, that is the distance between the transmitter and receiver. This is the reference distance. This D naught will be close to the transmitter. This n is the path loss component. Depending upon the environment, this n value will vary. So this says about the rate at which the path loss increases with distance. As the distance increases, this path loss will increase. So in decibels, this equation can be written like this. PL as a function of D naught plus 10 n log D by D naught. So as I said already, in this equation, this bar, it says that It is the ensemble average of all possible path loss values for a given value of t, that is given value of the transmitter-receiver separation. This n path loss component depends on, for a particular propagation environment, this n will have a specific value. As the environment varies, this n value will vary. Log normal shadowing. The log normal distribution describes the random shadowing effects. What is shadowing? It is the loss of signal due to the obstacles or disturbances present. So, this log normal distribution describes the random shadowing effects. This can occur over a large number of measurement locations. So, for the same TR separation, but at different locations we can measure, but having different levels of clutter. So, suppose if you take the TR separation is 10 meter, at different locations we can measure. So, in different locations, different obstacles can be there. So, this path loss is a random value and distributed log normally about the mean distance different value. So, it is distributed, it is a random value, it is distributed randomly and it is zero mean Gaussian value. So, this is a zero mean Gaussian value. So, it will be having a bell shape. If you plot the values, means it will be like a bell shape. So, path loss for a distance t having a unit of the decibel. This equal to average path loss at a distance t plus this Gaussian distributed random variable. This can also be written like this: path loss for the reference distance plus 10 n log d by t naught plus 0 mean Gaussian distributed random variable. How n and d are computed from the measured data by using linear regression. So, what is linear regression? It is an analysis of a set of statistical process, and why it is used means in order to find out the relationship between a dependent variable and one or more independent variables. So, actually this regression computes the relationship between the dependent and independent variable. So, by this the difference between a measured and estimated path loss is minimized in mean square error sense for different locations and different TR separations. So, we have to calculate n and d by using linear regression in order to reduce the measured and estimated path losses. Q function. It is called the error function. So, why this Q function is used means it is used to find whether the probability of the received signal is going to exceed or fall below a particular level. So, this is the equation of the Q function. Q of z is equal to 1 by root of 2 pi integral exponential of minus x square by 2tx, that is equal to half 1 minus error function of z by root 2. So, suppose if you want to calculate the probability of a received signal above a certain value gamma means like this, by using this equation it can be calculated. Received power function of distance greater than gamma is equal to Q of gamma minus average received power and function of distance divided by sigma. If it is less than gamma means this is used. Q of average received power distance d minus gamma by sigma. Next, small scale fading. So, what is small scale fading? It is a fluctuations or changes in the amplitude of a radio signal for a short period of time or short distance. how fastly the amplitude of the signal is going to change over a short period of time or short distance. Why this is occurring is because the signal is traveling in multiple paths. So the received signal is the summation of all these signals that is coming from different paths. So when they are traveling in a first path, it will be experiencing some sort of attenuation. In the second path, it will be different. So the resultant is also going to change. There are three important effects of this small scale fading. What is the impact means? The signal strength is going to change. Then frequency modulation is occurring due to the varying Doppler shift on different multipath signals. Then because of the multipath propagation delays, some echoes will be generated. So these are the three important effects. Signal strength is changing, frequency is changing, and time is different for each and every received signal. So echo occurs. Then these are some of the factors influencing the small scale fading. First one is multipath propagation. So multipath propagation, because of multipath propagation, that is reflecting objects will be there, scatters will be there in the channel. Because of it, there is a constant change in environment. So in one path, reflecting objects may or may not be there. In another path, it can be there. Scatters can be there. So the path is differing. So the environment of the signal that it is traversing, it changes. And as it passes to the path, as it travels a distance, some amount of signal is dissipated. So there will be a change in amplitude, change in phase and time. And not a single version of signal is going to reach the receiver. Even though we have transmitted a single signal, multiple versions of the transmitted signal will be arriving at the receiver. And they are displaced with respect to one another in time and spatial orientation. That is, the arrival time can be different and the distance traveled by each and every signal will be different. Random phase and amplitude of different multipath components. So they are traveling in different paths. So each and every signal will have a different amplitude. There will be phase difference between them. So this results in small scale fading or changes in the signal envelope. Then lengthens the time required for the baseband portion of the signal to reach the receiver. So one signal, if it is moving in a very good environment, means it will be reaching the receiver quickly. The other signal, if it is traveling in a cluttered environment, it will take time. So one signal will reach immediately, other signal will not reach immediately. So what will happen is that at the receiver portion, we take the resultant of all signals. So signal smearing can happen due to the delayed signal. Second, speed of mobile. So the relative motion between the base station and the mobile. This is the random frequency modulation, because when the receiver is moving towards the source, there is a change in the frequency felt. Similarly, when it is moving away from the source, a different frequency is felt. So this is called Doppler shift we say. It can be either positive or negative depending on whether the mobile receiver is moving toward or away from the base station. So thank you.